right, let's get started. So we have two talks in this session. First talk by Gilles Zémor on Kneser's theorem.
Thank you very much. So I'm going to motivate this talk by the study of L-divisible set families. The problem may look a little narrow, but I like to think that the methods aren't. The methods look to be much more general than that to me. So what are we looking at? There's this very classical and relatively simple problem that is sometimes called the Eventown problem. I'm not sure who invented the term first. I suspect it's Babai and Frankel, but I'm not 100% sure. Someone knows, please tell me. So the problem is this: you have a collection of objects that are a set of elements from 1 to n, say, and a collection of subsets such that the intersection of any two subsets has even cardinality. And you want the maximum size of such a family. So the answer is kind of simple. You view your subsets as 0, 1 vectors or functions, Boolean functions if you want. And you consider the linear code generated by your vectors, and you realize that the intersection property means that the product, coordinate-wise product of any two vectors has even weight, and that means that they have to be orthogonal. So the code has to be self-dual, it has to be included in its dual, so the dimension can't be more than half the length, n/2, and you can't get more than 2 to the n/2 elements in your family, and that's tight for many reasons. There's a trivial construction of family of subsets. You can partition your space into pairs of elements, and you take all possible unions of those pairs of elements, and you achieve the size 2 to the n/2. And if you're a coding theorist, you also know that you can do the same thing with self-dual codes, and there are loads and loads of self-dual codes. Classifying them is an impossible task. So that kind of closes things for this problem. And there's a natural generalization, which is all right. Now, what happens if you require of your subsets that every intersection has size divisible by 3, say instead of divisible by 2? More generally, divisible by L, then what is the maximum size? Well, nobody knows really. You could think that it could be 2 to the n over L, because if you try to do the same atomic construction, like your set of elements, you decompose them into packs of 3 and take all unions of that, then you see that you will get a family of size 2 to the n/3. But if you look a little more, you can get more than that. There's a larger example. You can get them with Hadamard matrices. So you take a Hadamard matrix of size 12, transform the rows into 0, 1 vectors. You can take a coset of that with by the all-1 vector. You get 24 vectors of length of 12. And if you look closely, the intersection of any two, or product of any two has weight divisible by 3. So 24 is more than 2 to the 12 over 3. And 2 to the n over L. Well, no, because you can replicate this counterexample. I mean, you can take a set of size 12 times whatever, 12 times n, and you will get a family of size 24 to the m, which is exponentially more than 2 to the n over 3. So we don't know what the real answer is. This problem is mysterious. But you can still get a result. And this work is inspired by this recent result of Gilles, Sudakov, and Salmon. If you strengthen the hypothesis to requiring that any k subset intersect in something divisible by L, then yes, you can't go beyond 2 to the n over L. Now the k that they required was probably very loose. It's a constant in the sense that it's a quantity that depends only on L, but the one that they derived is basically exponential in L and is more than the real thing. It still was a strong result. It solved the conjecture of Frankel and Lidlichko, which goes back some 40 years. So we gave it another look and reduced the size of k. So in particular, if L is a prime, and you only need to require the intersection of p different subsets to have size divisible by p to be able to deduce that the size of your family is upper bounded by 2 to the n over p. So for general p, still probably not the optimal result, but it is for p equals 3. Because as we've seen, requiring only that 2 subsets intersect in 3 or in number of positions divisible by 3 is not enough. So you need to go to at least intersecting 3 subsets to get a result of this kind. There's a companion result which says that if F is large enough, then only atomic families will do the job. You will not have the equivalent of some self-dual codes. And for general L, we can still get a result, but it gets looser. So the result says that if you require the order of L squared vectors or family members to have an intersection divisible by L, then you must have an atomic family, and again, the maximum size can't be more than 2 to the n over L. So it brings the value of k down from exponential in L to polynomial, but it's probably still far from the real thing. So method. So from the original Eventown example, you see that linear algebra methods are going to be involved, right? The natural thing was to consider the code generated by your 0, 1 vectors and try to say things about properties of this code. So there's one thing that is simple enough to say, which is that if your family has the required property, and call it, if it's k-wise divisible, L divisible, so let's say P divisible here, because let's focus on the case L prime, which is simpler, then it means that for any K which is in the case product of the code generated by your family, then X has to be orthogonal to the all one vector. If you, considering the space generated, the code generated by your 0, 1 vectors over FP. So a little more on this code product. Let me tell you or remind you what they are. We're considering the relevant product here is the coordinate-wise product, sometimes called the star product, the Schur product, the Hadamard product. So for vectors, it's just coordinate-wise products. And for codes, to get the product of two codes, you take all coordinate-wise products of the code weight of one and code weight of the other, and take the linear span of all that. And that gives you the code generated by this. And you can consider powers of a code. So the case power of a code, I'm using Rondria's notation here. Here, this reminds you of a linear span. So C to the power K is the iterated product of C by itself A times. Repetitions of what? Yeah. Yes, yes. Why couldn't we do that? Sure, we can take the product of C with itself. In this case, C equals T. So it's not too difficult to convince yourselves. You can see by doing some experiments that if you take codes C and D with no particular structure, then typically the dimension of the product is not going to be more than the product of the dimension. That's always true because you can generate the product by all pairwise products of two generator matrices. But typically what you have is that the upper bound is going to be close to the real thing. Or your product CD is going to fill up the whole space. But you have remarkable exceptions. Reed-Solomon codes are one such exception. And you have some others. And code products, shan't get into this, but they have many applications. Originally, they were introduced for decoding. They're also very useful in secret sharing, MPC protocols, oblivious transfer, cryptanalysis, also quantum computing. Yes? You mean, okay, I'm allowing the intersection of a set with itself. There's kind of a fine point. I didn't want to get into this.
But you allow that.
Yeah, I allow this.
Your condition is not cancelled.
Right, I'm allowing this. Actually, the original, since you mentioned it, the original conjecture by Frankel and Idlischke actually disallowed this. But what Gilles et al. Proved is that the two problems are really very close. If you can get a theorem allowing self-intersections, then you will also get a similar theorem with the same value of k that doesn't allow intersections. It's kind of non-trivial, but they have a clever way of doing this. So you can kind of forget this issue of allowing or disallowing self-intersections and just focusing on the case when you do allow self-intersections, which is much easier to deal with when you're applying linear algebra techniques. Little advertising for this theorem, which really comes in very handy. So how small can the dimension of a product of code get? It can be very small. For example, if you have a trivial generated matrix which looks like this, for example, little blocks of ones and zeros elsewhere, well, you can see that if you take the product of this code with itself, it's just the same code. C squared equals C. Right, but this example is really unavoidable in a sense. In what sense? In this sense. So the dimension of the product is always going to be larger than the sum of the dimensions minus the term S, which tells you in how many disjoint blocks the product CD breaks into, in how many disjoint subblocks. So if you have a certain value of S here, it means that the product of your two codes has to break up into a direct sum of at least S codes with disjoint supports. And really, this is a version of Kneser's theorem for abelian groups. So what does Kneser's theorem for abelian groups tell you? It tells you that if you look at the cardinality of the sum of two sets, it's always at least larger than the sum of the cardinalities minus the cardinality of a subgroup, which is the stabilizer of the sum. So it's the set of group elements that leave the sum invariant. And really, this type of code, it's the equivalent of a subgroup in a code setting. So FP to the n, it's a linear space, but you can also think of it as an algebra for the coordinate-wise product of vectors. And the code generated by this is not just a vector space. It's a subalgebra. If you multiply elements of this code by other elements of this code, you stay in the code. So the more precise version of Kneser's theorem for codes says that the dimension of the product is at least the sum of the dimensions minus the dimension of the stabilizer, which is the set of vectors that multiplied by the code stay in the code. And it's not too difficult to show that stabilizer subalgebras, the stabilizer of the code, it's generated by a set of constant vectors with disjoint supports that exactly tell you how your code CD breaks up into a direct sum of small codes. So why is all this relevant to the KY's L divisible problem? to bounding the size of k-wise L-divisible families, because now you can introduce this sort of argument. So you take the vector space generated by your 0, 1 vectors over FB and call it V, and you consider the sequence of iterated parents. Now, either the dimension of the elements in the sequence grows too quickly, and then it's eventually going to fill up the whole space, and that's obviously not possible if you want your elements of b to the k to have weights divisible by p, or Kneser's theorem is going to tell you that the sum of some term here, some v to the I plus 1, its dimension is not going to be sum of the dimension of the I plus dimension of v. And this, if you look closely, it carries over to the end term, v to the k. Kneser's theorem is going to tell you that this term splits into a direct sum of spaces, each of which is orthogonal to the all-one vector. And that breaks your family into basically two subfamilies, each of which is going to have to be k-wise p divisible. I'm making the argument a bit quick, but this is the basic idea. And then you can use an induction argument to tell you that this is not possible if the cardinality of F is too large. You need an extra ingredient to apply this reasoning. You need something which tells you what is the dimension of the space V generated by a set of 0, 1 vectors. And there's this relatively simple argument that tells you that take any vector space, say in FP to the n, and you want the number of 0, 1 vectors in this vector space. Well, it can't be more than 2 to the dimension of V. So this almost gives the optimal result for p equals 3, but not quite. We had to work some more. Yes, sorry. Exactly, yes. It should be 0, 1 to the power then, yeah. So we needed to bring this down to 2 to the r minus 1 to get the whole argument to work for the optimum p equals 3 result. Probably I'll go over this very quickly. This was the outline of the argument for prime P. If you're studying L-divisible families for L which is not prime, then it gets a bit more messy. So if L is, say, a product of primes, then, okay, you have to consider several spaces V generated by your original family of 0, 1 vectors. You have to consider the subspaces over all the FP where P is a divisor of L. And you're not sure that these different spaces will behave nicely relative to each other. In particular, if they break up into a direct sum of codes, there's no a priori reason for these direct sum of codes to be the same for different primes. So you have to adopt a different strategy that was also adopted in Sudakov et al.'s paper, you're trying to focus on proving the existence of an atom of F, meaning a subset on which, a maximum size subset on which your family F is constant. So you're looking for an atom which is divisible by all the P's that divide L. And to do this, you apply Kneser's theorem in your different vector spaces generated by F. I won't say any more because it really gets technical, and the core ideas are already present in the in the prime case. There's also the issue of what's going on. What can you do when you have powers of primes here? I'm not even mentioning the horrible things that you have to do in this case. It's time for me to conclude. So some intriguing questions. So for this P equal 3 case, what would be the largest non-atomic 3 divisible set family for a given length n? And there are many questions regarding code products. So for binary codes are the more intriguing case. Here we have an interesting intermediate case where we're considering codes over FP for a prime P that's allowed to be big, but you want codes that have a basis of 0, 1 vectors, and it kind of changes the picture. You can't have read-solved codes, for example. I'm out of time for me to share thoughts on what could be happening beyond Kneser's theorem and what sort of candidates you have to get codes of small products of small dimension. But if you're interested in the subject, I'm happy to talk about it anytime. Thank you for all your attention.
This small example.
That would be a way of constructing large examples, but why? I mean, there could be increasing families. I don't know whether it's going to be given by the best small example, maybe, but why? True. True. And I was also vaguely fantasizing that there'll be an HDX connection, because there's kind of a geometric field to the problem. After all, if you take, I don't know, families of hyperplanes, then all their in some geometrical space, then typically all their pairwise, 3-wise intersections will have a fixed cardinality, but they're not very large families. So how do you go beyond that?
Yes. So would you conjecture that maybe the behavior of the A equal LDPC opposite if you think you need a larger
I have no idea. I don't know. I'm not confident that k equal 3 wouldn't be enough for all values of L. I have no counterexamples. I don't know. The case when L is a prime power could be possibly quite different from the other cases, but I don't know. No. Yeah. Yeah, but I guess that he's asking for L equals 3. I don't know of any other counterexamples. I'm not sure any are known. I haven't come across anything else in the literature. I very vaguely tried to construct some other examples with HDXs, but I didn't come close.